Hello all. So as a continuation of my lecture series in transmission and distribution, the upcoming video is about parameter calculations to design a transmission line. So in the previous videos we have seen about the conductor selection and the choice of the conductor, and here we are going to talk about the parameter calculations and what are all the assumptions that we have to do before designing a transmission line. So the contents in this video will be assumptions to use formulas for convection and radiation. So what are all the assumptions that we are considering? Next one is choice of span and spacing between the conductors and sag tension calculations for overhead lines. So sag and span are very important for a transmission line. So first assumption is for using the formulas of convection and radiation, it is necessary to assume total conductor temperature, air velocity and surrounding temperature, because overhead transmission line is going to be in a open space. So it is not going to be in a closed space. So first we have to consider about the temperature of the conductor, air temperature and surrounding temperature along with the air velocity. So what is the velocity of the air which will be falling on the conductor line. So this is very important. Based on these values, the current carrying capacity of the line can be determined. So this is the procedure used for designing the conductor size. So conductor size is designed with the help of this and with the operating voltage of 220 kilovolt. And the other assumption is, in case of extra high voltage or ultra high voltage lines, radio interference and corona effect should also be taken into consideration. Such conductors are usually thick, so thick in size. So using bundled conductors, corona and radio interference is economically reduced. Bundled conductors is with 2 or 4 subconductors are commonly used. So bundle conductor is a combination of 2 or 4 subconductors. So if we use a bundle conductors type, then corona and radio interference can be economically reduced. And span. So choice of span. So in line span is long, then number of towers will be required, but the towers will be taller and expensive. So the longer line span is used for higher operating voltage, so that high cost of insulators is reduced. So with appropriate lifespan, the cost of the line will be minimum. So we have to plan the lifespan of the transmission line improved by reducing the number of towers and selecting greater lifespan. So with this appropriate lifespan only, the cost of the line will be made minimum. So see, this is the span length. S is span length, that is distance between two towers. So L is conductor length. So how much meter of conductors which we are going to use, and this difference between the span length and the conductor length, we call it as sag. That U-shaped structure is called as sag. So we have here same level support, that is both the poles are at the same level. So for hill stations, if we see, the one of the tower will be in the top and one of the tower will be in the bottom. So that is not at the same level, it is of different level. So the calculations will be changing when we design a mechanical design of transmission line at that particular place. So this is for a plain area. So the height of the tower and lifespan are not that only influencing factors of cost, but it also causes lightning hazards increases, which considerably increases the height. Nowadays, a lifespan of 200 to 400 meters is used for high voltage lines, while for river and ravine crossing areas, it is of order of 800 meters. For 400 kV lines, the lifespan will be a range of 350 meters to 400 meters. So if you are going to transmit a 400 kV line, then the lifespan will be of a range of 350 meters to 400 meters to place the poles. Spacing between the conductors. So the most suitable spacing between the conductors can be arrived with the help of mathematical calculations. So it cannot be just like that planned. We have many mathematical calculations which we will be discussing in the upcoming videos. So the spanning between the conductors, so the sag in meters and line voltage has to be considered in order to define the spacing between the conductors. So for a line, for a line voltage of 0.4 kilovolt, the spacing should be 0.2 meters. Similarly, if it is 765 kilovolt, the spacing should be 14 meters. The spacing between the conductors, that is, if we have a three-phase line, the spacing between each conductor should be of this table, this range of table. And sag tension calculations for overhead lines. So see, it is clearly seen, this is the conductor and that is span and sag. So it is based on the fact that when a wire of uniform cross section is suspended between 2 points at the same level, then the wire sags down and assumes the shape of a parabolic, or we call it as catenary shape. So this shape is called as catenary shape. The main factors in the design and stringing of conductors on the supports are the conductor load per unit length, conductor tension, span distance between the supports, and temperature. This has to be considered. These are the main factors. And for determining the conductor load, the weight of the conductor, weight of the ice or snow clinging on the conductor, and wind blowing against the conductor, because as I have already said, the transmission line is in a free open space. So we have to consider all the surrounding things like ice, snowfall, and wind blowing against the conductor. All these parameters has to be considered. So the sag is independent of what? It is independent of line voltage. So sag does not happen since there is a higher line voltage. So sag is independent of line voltage, and if supports are equal levels and tension in an overhead line is increased 2 times, then sag decreases to half of the previous value. The sag decreases to half of the previous value. Thank you.